All right, welcome to lesson 5.8. So today we're looking at integrals and exponential functions. So you might recall from unit 2 that the derivative of e to the x was simply e to the x. So it shouldn't surprise you then that the integral of e to the u du is simply e to the u plus c. So because you are more than likely to encounter e to the u with a substitution, that's why it's written in terms of u already. So when you are integrating involving exponential functions, again, most often, I'd say 99% of the time, your choice of your u is going to be whatever power is on that exponential function. If it's anything other than just an x. Again, 99% of the time, that's what you're going to want to do. And yes, we will see an example where it's that other 1% of the time. Okay, so we're going to just go ahead and look at a few examples of integrating with this, including an example that's going to be finding a definite integral that involves an exponential function. So let's go ahead and take a look. All right, so let's start with the integral of e to the sine of x over secant of x dx. And as I said before, if you're unsure where to begin in terms of substitution, your first instinct should be that I have e to a power other than just a plain x, so my first instinct should be to try letting u equal, in this case, the sine of x, whatever that power is. So that would make du equal cosine of x dx, and that would make dx equal du over the cosine of x. So now when we substitute, that means we're going to have e to the u over the secant of x, and then that gives us a du over cosine of x. Now the secant of x and cosine of x, maybe that's not jumping out at you, maybe it is, but remember that secant of x in the denominator is the same as having a cosine of x in the numerator. So this is what we actually end up having, because remember cosine and secant are reciprocal functions. So those cosines do divide out, and now we have the integral of e to the u du, and there's our basic antiderivative for the exponential function. So we do know that that's just going to give us e to the u plus c, and then of course we substitute back in for u, and we get e to the sine of x plus c. And that's that. All right, let's take another look at another example here. So this time we have the integral of e to the 1 over x all over x squared dx. So once again, hopefully your instinct is telling you that we should consider letting 1 over x, because that's the power, be our u. So if u is 1 over x, which again we can rewrite as x to the negative first, then that would make our du become a negative 1 x to the negative second dx, which we could then rewrite as negative 1 over x squared dx. And that means when I solve for dx, I'm going to multiply both sides by a negative x squared. So I get negative x squared du. So now when I substitute, I have e to the u over x squared, and then times a negative x squared du. So those x squares do divide out. I do still have a negative that I can move out in front, so let's go ahead and do that. So I have a negative integral of e to the u du. And once again, there's our basic antiderivative. So that's just going to become a negative e to the u plus c. And then I can finally substitute back in, and I get negative e to the 1 over x plus c. Okay, so those two examples that you just saw, those were part of that 99% of the time that I was referring to. Here's an example of that 1% of the time where your u is not going to necessarily be the power on your exponential function. And how would you recognize it? Well, there isn't really any one way, unfortunately. All I can suggest, though, is to try to recognize problems that look similar to what you've done before. So I'm showing you this example so that you can see this sort of for the first time. So notice we have an e to the 2x both in the numerator and in the denominator. And if I were to let u equal 2x, all that's really going to happen is we're going to get a different constant floating around in there, and then we're going to have an e to the u and a 7 plus e to the u, which really doesn't make this any better for us. But what if we were to let u equal the entire denominator of 7 plus e to the 2x? Well, then our du becomes, so the derivative of that, remember, derivative of a constant is just 0. And then the derivative of e to the 2x becomes e to the 2x times the derivative of 2x, which is just 2 dx. And then when I solve for dx, I get du over, I'm going to go ahead and put the 2 first, over 2 e to the 2x. So now watch what happens when we substitute. So remember, e to the 2x, I didn't do anything with that, over u, because remember I let u equal that entire denominator, and then my dx turns into a du over 2e to the 2x. And now that e to the 2x divides with that e to the 2x, and then this 1/2, because remember there's a 1 up there, that 1/2 I can move out in front. So this now becomes 1/2 times the integral of 1 over u du. And in light of the previous lesson, hopefully the integral of 1 over u is something that you're familiar with. So this does now become 1/2 times the natural log of the absolute value of u plus c. And let's go ahead and substitute back in for u. So I have 1/2 times the natural log of the absolute value of 7 plus e to the 2x plus c. But remember, the absolute value of 7 plus e to the 2x, remember the absolute value is only there as a safeguard, but e to the 2x is never going to be 0 or negative. It's always positive. And then plus we're adding a 7 to that, which means this is always positive for sure. So that means the absolute value is unnecessary. So we have the natural log of just 7 plus e to the 2x without absolute value. And then remember, with our log properties, that 1/2 can come back up here as our power, and we can finally rewrite this as the natural log of the square root of 7 plus e to the 2x plus c. And of course, again, like I keep saying before, if you did leave this answer here, that's fine. It's okay. It's just not the best. All right, so again, that was an example of sort of that 1% of the time when letting u equal your exponent on the exponential function isn't necessarily the way to go. All right, and finally, we're just going to wrap up here with a definite integral that involves an exponential function. So, same idea. The only difference is I have a definite integral this time. Still have to figure out my substitution. I have x squared e to the negative 2x cubed. So, once again, my instinct tells me let's try letting u equal that exponent. So if I let u equal negative 2x to the third, then that would make du equal negative 6x squared dx. And so my dx becomes du over negative 6x squared. But remember, because this is a definite integral, and like you just saw in lesson 5-6, I also need to change my limits. So when x is 0, my u is going to become 0. And then when my x is 1, my u is going to turn into a negative 2. Now you saw this before. Remember, my upper limit is now going to be smaller than my lower limit. Do not just change it because that makes you feel like it's in the wrong order. You have to stick with the order from the original problem. So this now becomes the definite integral from 0 to negative 2 of, and then we still have the x squared there for now, and then this is e to the u, and then the dx becomes du over negative 6x squared. Those x squares do divide out. The negative 1 over 6 we can move out in front. And so now, finally, this is what we have. So now we can finally integrate. So I have negative 1/6 times, well, the antiderivative of e to the u is just e to the u from 0 to negative 2. So now I've got negative 1/6 times e to the negative second minus e to the 0. But remember that e to the negative second is really just 1 over e squared minus e to the 0, which is just a 1. But 1 I'm going to rewrite as e squared over e squared to get a common denominator. So now I've got negative 1/6 times 1 minus e squared all over e squared. Again, I got a common denominator, so I can combine those two terms into a single fraction. And then finally, I'm going to multiply that negative 1/6. Now, in the denominator, that 6 is just going to multiply with the e squared, so in my denominator I have 6e squared. In the numerator, that negative multiplies in, so I'm going to have a negative 1 and a positive e squared. So I'm just going to reverse the order, so that's going to give me an e squared plus 1. Sorry, minus 1. There we go. And that's it. All right, so once again, for integrating involving exponentials, 99% of the time, consider letting your u equal the exponent on the exponential. Sometimes, though, that won't be the case, and again, you'll just have to sort of experiment a little bit with some other ideas that you've had in the past for choosing your u. All right, good luck.